spectroscopic properties. It's just the spectroscopic. Got it. Yeah, sorry.
Yes, sorry.
Yeah, so it shows the spectroscopic properties of some of these transients around the time of maximum light. And then, so this is basically a set of core collapse supernovae. There's no type 1 in there, showing the presence of the hydrogen Balmer lines and the Doppler broadened because of the fast expansion of the ejecta. There's one outlier here, which is an interacting supernova. And we go back to the point, why do we see narrow lines in this object? And basically, from the information you have encrypted in the spectrum, you can deduce the expansion rate of the ejecta, the composition, the ionization, the temperature, and you can basically build a comprehensive picture of why this object exploded or how it exploded and where it came from, how it evolved from the main sequence. The Lie curve diversity is telling you something about the energetics. So you can integrate the Lie curve over time and see how much radiation was emitted from the object, compare it to the kinetic energy that you might infer from this. And then what you see here is that there's a huge range in timescales, from a week timescale to several month timescales, and a huge range in brightness. Eta Carinae, which is the most famous most famous star in the galaxy after the sun, was in outbursts at -14. And so all these objects are way up, and these objects reach peak luminosities of 10 to the 10, 10 to the 11 solar luminosities. So they're really exceptional. So I will focus primarily on massive star evolution in this talk. So if you want to do a very simplified explanation of what happens in massive stars, you can basically view a massive star as being changing its properties in the core and at the surface. So there's an evolution in the core. Basically, you start from a prime order composition, which is hydrogen and helium, with solar metallicity typically, and then you're going to fuse the nuclei. You basically form nuclei that are more and more bound. You extract binding energy from these nuclei, and then you can go stably or not stably all the way to an ion core. So the energy released from this nuclear burning provides the thermal pressure to support the star against gravity and provide the stellar luminosity. So you have various transport processes for taking out the energy from the core all the way to the surface. So during hydrogen and helium burning, you do this with convection and transport by photon diffusion, radiative diffusion. And after you start carbon burning, there's a major coolant, thermal coolant through neutrinos, and this becomes very important. It actually leads to a complete change in the evolution of the star. Basically, there's some sort of runway. The various burning stages become shorter and shorter. So a massive star will spend 90% of its life burning hydrogen in the core, but it will spend only 1 day doing silicon core burning. So it's extremely rapid. And there's also some various processes that will bring some of the metals produced in the core all the way to the surface, which can be used as diagnostics for understanding what happens in the core. At the surface of the star, you have a luminosity that basically is the obvious counterpart to the nuclear luminosity in the core. The luminosity is very large, 10 to the 5, 10 to the 6 times the solar luminosity. And the typical mass loss rates that you have are the order of 10 to the 5 solar mass per year, except for Wolf-Rayet star, hydrogen depletion stars, compact, and 10 to the -6 solar mass per year for red supergiant stars. The material is littered on the surface through a radiation driven, which basically is transfer momentum, radiation momentum from the material to the gas, and so you drive material away. In the binaries, you have a possibility of having an interaction with the companion and transferring mass at much larger rate, 10 to the -3 solar mass per year, either stably or dynamically. And so there's potential for losing a lot more mass. Okay, so at the end of the evolution of the star, you end up with a massive star which has an iron core. It's basically a white dwarf made of iron, and this iron core is going to collapse. It doesn't collapse because you're running out of fuel to burn. This thing is supported by electron degenerate suppression, and it's pretty happy to be there. But it will collapse because of electron capture on nuclei, because of photo disintegration, and also because at the top of the iron core you have silicon burning shell that keeps adding material to the iron core. So eventually the iron core becomes too massive. It overcomes the Chandrasekhar mass and it collapses on the dynamical time scale. So this is pretty short, 10, 100 milliseconds. And it will collapse all the way to nuclear densities. So when the central density reaches 10 to the 14 grams per centimeter cube, you have a bounce, it's what we call core bounce. There's a formation of a shock wave, and the shock wave moves out. This process is not adiabatic. There's a lot of energy losses associated with this. come from the electron catchers again that will give rise to a gigantic neutrino burst. And also photodisintegration behind the shock is going to, so you have dissociation of the nuclei, and that's also taking out energy. And so eventually the shock, instead of having a bounce like dropping a tennis ball on the ground and it goes back to your hand, in fact, you drop the tennis ball and the ball just basically barely lifts off the ground because it lost too much energy in the process. This is what happens in the neutron star. Basically, a lot of energy was lost. So the shock stalls, and it's revived on a timescale of about 1 second by energy deposition by neutrinos. And so eventually you have an explosion. We know we have an explosion because we see this supernova in the sky. And eventually the shock is revived and goes all the way to the surface. Okay, the time scale for reaching the surface of the star depends on the size of the star. So if it's a Wolf-Rayet star, it will take a very short time. If it's a red supergiant star, it will take much longer, typically 1 day, because the envelope is very extended. So even though the neutrino burst or the gravitational waves that are associated with the formation of the neutron star, basically define the time of explosion, actually the first electromagnetic display that you get from the supernova, the photons, arise when the shock emerges at the surface. So there can be a very large time lag between the two, up to a day, something like this. And at the time of shock breakout, the shock has left a structure that is a bit peculiar. All the energy is not kinetic. 50% of the energy is actually internal, and it's radiation. And this is very important for understanding some of the things I will say later on. This radiation is trapped behind the shock, and we do work to expand further the material until it reaches homologous expansion. This is when the velocity becomes roughly proportional to r. And then each mass jet is just going along ballistic, has a ballistic trajectory. It moves at constant speed. Typical properties that you have for this explosion, this is generic for core collapse supernova. Can vary this by a factor of a few, but the generic value is 10 to the 51 ergs for the kinetic energy of the ejecta. There's a nuclei. The nucleus here, 56 nickel, that is produced explosively in these explosions, is absolutely central for providing the brightness of type 1a supernovae through radioactive decay. It's an unstable nucleus. Is secondary for type 2 supernovae or type 1b, 1c, core collapse supernovae. And it's also secondary for providing the energy of the explosion. Most of the energy in core collapse supernova comes from neutrino energy deposition. This is what we believe. So the evolution that you have after shock emergence is essentially an energy problem. You want to understand how this ejecta is going to cool, how it's going to be heated up by various processes like radioactive decay. And the mass of the ejecta and all these various parameters will define the diversity, or will control the diversity of the light curves in the spectra that you see. The subsequent evolution has basically two phases. There's a photospheric phase when the ejecta is optically thick, and then eventually, because of expansion and cooling, turns optically thin and you enter the nebular phase. So this is a plot here for a type 2 plateau supernova. That's a red supergiant star explosion, like Betelgeuse, we think. That shows the spectral evolution in the optical from 10 days after explosion, the inferred time of explosion, up to late times in the nebular phase, about 2 years. So at early times, you see a blue spectrum, suggesting that it's quite hot. It emits like a black body, modified black body. And then you have these binary lines. This is H-alpha, H-beta. And they are Doppler broadened by the fast expansion of the photospheric layer. You're looking at the outer parts of the ejecta. And as time goes on, the ejecta expands, cools. You have the appearance of these iron 2 lines. This is what we call metal line blanketing. That's a forest of iron 2 lines that will absorb the radiation emerging from the photosphere. And then you see a recession of the emitting layers. So the lines narrow in time until you reach the nebular phase, when the lines pretty much stay the same width, but they change in shape. You no longer have Pissigny profile, but you have these emission lines, forbidden lines, basically produced from the collisional excitation and radiative excitation of low-lying labels, so tied to the ground state. So there's oxygen 1 here, this is calcium 2. They are notoriously seen in those objects. So obviously here you probe at early times the outer parts of the ejecta, what used to be at the surface of the massive star, and at late times you probe the core. So what was impossible to see earlier on when you had the star. So the object I've just shown has this line curve. This is the green one here, and this is why we call it a type 2 plateau. This is the V-band magnitude, absolute magnitude as a function of time. So they're plateau because they're completely flat. In fact, when you look at the full diversity of type 2 supernova light curves, you see a lot of diversity. Some of them are fainter, and we think that's just because the explosion energy is smaller. So there's the engine that produces the explosion does not operate as efficiently in all objects. But there's also these weird objects here that have much larger brightness, much larger luminosities. You have some extreme examples like this object 2009 IP. And this object is actually very peculiar in many ways. The first one is that it was defined a supernova in 2009. And that's the clock here when this definition was made. But then the object had this very erratic evolution and even became much brighter 3 years later. So in fact, this object was defined as supernova, but then 3 years later, it was still exploding. And it just shows that we keep being surprised by some of these massive stars because they have not a terminal explosion, but they have repeated eruptions. And 2009 IP is an object that potentially is similar to Eta Carina in a way. So this is Eta Carina that you see here. You can see that these variations are very, very strange. I mean, how can a star do, well, yeah, how can an object vary on time scale of 10 days a month, with variations in factor of 10 in luminosity? And so we think that this is directly related to interactions.
What happened to this object afterwards? Because here it stopped in 2000.
So yeah, so people are still observing it. Sorry, people are still observing it, and still going. Today we see H alpha in emission in the spectrum, optical spectrum. The brightness is very low, and it's not clear. So one of the mechanisms that we'll talk about at the end could be pair instability pulsations. We could have recurrent mass loss episodes that leave behind a remnant star, and the star is still there and it's still luminous. So it's not clear whether you're looking, for example, at the stellar wind that arises from that massive star, whether you're looking at an ongoing interaction. So we see. So this is for the likers. For the interacting supernova, the one thing that is the defining property is the spectral shapes that we see in the optical. So to put simply, if the basic reason why a supernova is luminous is not because it's hot. The typical color temperature of a supernova is the same as the sun. So they're cool plasmas. And the reason why they're so luminous is because they're gigantic. They have photosphere that are 10 to the 15 centimeters. They're 100 times the size of a red supergiant star. And so one thing that you immediately wonder is, how do they get to such large radii? Well, it's because they expand very fast. And this is why, and what confirms this, is that the line profiles are very broad. Now we have this very peculiar situation where we have objects that are even more luminous, but when you take a spectrum, they have narrow lines. So then you wonder, well, how can they be more luminous? They have pretty much the same color, but they supposedly move slowly. How can you get to large radii if you move slowly? So the idea is that you form the photosphere at large distances. So basically, there is some episode of mass loss that puts the material at large distances, and then you have an explosion that smacks this material and forms the photosphere at 10 to the 15 centimeters or larger. And the reason why you see these narrow lines is because the radiation from the shock, from the supernova impacting the CSM, is entirely reprocessed by the CSM. The CSM is not yet shocked and accelerated, so it's moving slowly. And the typical imprint that you have in there is slow motion, perhaps partially ionized material. And the lines have this peculiar shape here because they're modified by electron scattering. It's actually a process that operates in blue supergiants, for example, like Eta Carina. And this process of electron scattering is something that occurs whenever the expansion rate is small. And so if you have an ionized plasma rich in hydrogen, there will be lots of free electrons around. At 10,000 degrees, these electrons will move at 500 kilometers per second. So this is quite significant, especially if the material is moving otherwise at 10 or 20 or 50 kilometers per second. Basically, you have a thermal motion of particles that is much larger than the bulk motion of the material. And if the optical depth is large, the photons will have to interact with these electrons before coming out. So every time there's an interaction with the electrons, you can have non-coherent redistribution of these photons, so that they basically shift in frequency, and they can shift equally because it's statistical. They shift equally likely to the blue or to the red compared to the rest wavelength, and this is why the lines look like this, quite narrow with extended wings and symmetric profiles.
Sorry.
Yes.
Any of these very peculiar, supernovae had a GRB? Are you aware of it?
Well, so I mean, GRBs, so they're very rare. I mean, these things are very rare, but GRBs are very rare, but they belong to a completely different part of the parameter space.
But then
So
at the end, they come also from SN. So, I mean,
yeah. So, but we think that
some of them at least.
So we think that the fundamental engine behind GRBs, I mean, certainly the supernova associated with GRBs, is fundamentally tied to fast rotation in some hydrogen deficient compact, quite compact stars at low metallicity because they need to retain the angular momentum and the risk. And most of these stars are supergiant. They have lost in their rotation, and they lose mass, so they lose angular momentum, and they're also very extended, so they can't keep up with fast rotation. And then the engine behind this, that it doesn't seem that the explosion energy is very large in these objects, and it's just that they extract kinetic energy. I will come back to this in a few minutes. But in GRB supernovae, the idea is really the engine of the explosion that is really energetic. You have typical kinetic energies in the ejecta of 10 to the 50 keV, something like that, which is 10 times the typical value that we have in those interactive supernovae. And so if you look on the longer time scale for such objects, you also have a peculiar evolution. So for example, in 98S, same object, it developed this spectrum at late times. There's essentially one line. It's very, very broad. It's 15,000 kilometers per second, full width at maximum. It's suggestive that you have an interaction at large distances, basically in the outer parts of the ejecta. Basically, there's ongoing interaction. Well, so I would do two more cases on the observational side. So this is another type 2 plateau supernova. This is taken from a paper. It's not so easy to see, but the light curve, the V-band light curve is the yellow thing here. And it's not particularly luminous. It's at about -17. It's very typical of a type 2. And it also looks very similar to the type 2 plateau supernova. There's not like a huge peak in the brightness at early time. But the spectral evolution is very unique. So again, you have these narrow line profiles, symmetric, these central peaks. And the thing that is really spectacular about this object is that the ionization is very large. It's 0.6, 0.5. We have even 2 for a bunch of, in a number of these spectra. And this phase is very transient. After about 2 days, it's completely over. And at later times, the object develops into normal type 2 plateau supernova. So this is suggestive that you have an interaction that is very short-lived, but gave rise to these very high ionization, highly ionized lines. I talked in a coffee lunch about this object, 20 TLF. So I was part of this work with people from Berkeley. And here what you see is the light curve. So this is the phase when the supernova was detected. So the supernova was detected somewhere around there, and then they had very good photometric follow-up of these things. This is the photospheric phase, the nebular phase, and you see this huge boost to the luminosity. So this is the V-band again, and you have a boost at early times. It's not as flat as it used to be. But the thing that is spectacular about this object is that there was pre-supernova activity recorded by Atlas, which is one of the surveys, for about 150 days. And so this was magnitude -12, -13. And so this object clearly was non-standard. When you turn this into blackbody properties, this is the light curve that you obtain. So this is the boost to the luminosity at early times, and then you have this quite standard type 2 plateau light curve, then it turns nebular. And then this pre-supernova activity is at a rate where the luminosity is 10 to the 40 ergs per second. So that's a few times 10 to the 6 solar luminosity, 10 to the 6 times the solar luminosity. Yeah. And when you inspect the radius and the temperature associated with this blackbody, this temperature is quite small, it's 4,000 degrees, but the radius associated with this is 1 or 2 times 10 to the 40 centimeters. So it's basically, there's no star known in the universe that has this type of radius. This object is clearly undergoing something very major. That has nothing to do with hydrostatic equilibrium in steady state star, something that is well behaved.
I have a question.
Yes.
Do you have an idea why there seems to be two on the Flux plot? So there seems to be two regimes on the decay of the light curve?
Yeah. So yeah, indeed. So there are 2 regimes in the decay of the light curve. So in those supernovae, explosions of red supergiant stars, what you see here is primarily the release of stored energy in the ejecta. So the shock, when you get, as I said earlier, when the shock gets to the surface, it has left a lot of energy in the ejecta. So that's the ejecta is completely optically thick, and it's going to release the energy of a certain time scale. And in that object, that release stops here. This is when the photosphere has receded all the way to the center of the ejecta, and there's no more energy to release. So there's this sudden step. Then here, there's no more diffusion of radiation. There's no more time delay in the radiation from the supernova. What you see here is this power is exactly equal to the total power released by radioactive decay of 56 nickel. And you get a slope here that is typical of the decay power from 56 cobalt. Actually, it's not nickel. So nickel decays to cobalt 56 and cobalt 56 to iron 56. And here, this is exactly the slope at which it decays. It's the basic exponential. And so what is suggestive is that there's complete trapping of the gamma rays. So it's optically thin to optical photons, but it's optically thick to gamma rays. And so the gamma rays are still being trapped in the ejecta here. Yes.
Nice question.
Yes.
So 10 to the 14 centimeters, it corresponds to what kind of radius in layman units?
In layman units,
like a Mars orbit, like a Neptune
orbit,
or
so
like even larger, I guess.
I don't work on planets, well, no. So this is this is quite big. The sun is 7 × 10^10, 1,000 times the solar radius, 7 × 10^13. So you multiples of that. The biggest red supergiants probably are around 1,000 times the solar radius, 7 × 10^13. So you're a few times larger than this, and it's optically thick at that radius. So there's material there, and there's probably material beyond that. It's just recombined and optically thin, but there's material.
Do you have any estimation of the total matter in this?
Yeah. So this comes next. So the spectral evolution of this object is similar to what we've seen earlier. You have these narrow lines. So this is again 20 TLF, the same one for which we've seen the photometry. And you have these narrow lines early on, and then it develops. So there was a big gap here. We could not observe the object. It was behind the sun, but then we could observe it here, or it was too low on the horizon. I can't recall exactly, but it was unobservable. And when you take these later spectra, they look very similar to standard type 2 plateau supernova spectra. They're a bit bluer. And these observations at late times are unique in those objects that have an interaction. This is very rare because very often the interaction keeps going and we can't see these lines are basically drowned by continuum photons. But here you can see some metal lines that will help us characterize the mass of the progenitor. And what you can see here is that this line, which is oxygen 1, is quite weak compared to the H alpha that's next to it. Okay, so one thing that you can wonder is why are interacting supernovas so luminous? And it comes from a basic fact, which is that the typical representative kinetic energy in an ejecta, 87A and so on, is 10 to the 51 ergs, while the time integrated volumetric luminosity is on the order of 10 to the 49 ergs. And so whenever you have an interaction, you can basically take a little bit of that energy and put it in there. What you can see is that if you take 1% of that, you can double this. So if you take 10% of this, you will multiply this energy by a factor of 10. And so it's really the imbalance between kinetic energy and radiative energy in standard supernova that allow interacting supernovae to be superluminous. And a further thing that happens here is results from the fact that the bulk of the kinetic energy is stored in the outer parts of the ejecta. So this is a figure here that shows the mass fraction for a type 2 plateau supernova as a function of mass. So you have a hydrogen, and this is helium, oxygen, and so on. Dotted line is the velocity. So the bulk of the mass holds basically is at low velocity, and the fast material is at the surface of the object. If you integrate the normalized kinetic energy integrated from the surface here, you get to 50% of the total kinetic energy within 1 or 2 solar masses of the surface. So what it means is that if I was to put 1 solar mass of material here, I could extract about 50% of the kinetic energy. It will act as a dumper for the ejecta. And so, this is quite easy, quite easy. In a way, you basically have the ability of extracting the energy when it's most abundant, by adding mass. The second thing that is very interesting about these interacting supernova is what they do to the radiation because of optical depth effects. So this is another diagram here that aims to represent the optical depth variation when you go from the inner parts of the ejecta or the star to the surface layers. This is around the photosphere, and this is in the environment, which may be a tenuous atmosphere or a CSM. So the optical depth is huge in the inner parts of your star, the envelope. And as you get to the photosphere definition would be optical depth 2/3, and so on. So when your shock is born here at the surface of the neutron star and starts crossing the envelope, there's a lot of radiation behind the shock, but the mean free path for these photons is very small. So basically the radiation is just advected with the flow. It's not going anywhere. But when and in other words, what it means is that the shock propagation time is extremely rapid compared to the diffusion time of this radiation. So there cannot be any diffusion. But when the shock gets to an optical depth of about 10, it takes actually a shorter time for the radiation to get out of the star than it takes the shock to get out. And so this is when you have a radiative precursor. What it means is that there are photons behind the shock that will start leaking out of the shock when you are around this optical depth. Now, depending on the length scale that you have to go between optical depth 10 and 1, you can have a short precursor or very long precursor. And the thing is that if you add material here with a lot of circumstellar material, what you can do is basically extract more and more of this radiation that is behind the shock, because you allow the leak to be much greater. So the longer you will allow this leak to occur for, the greater the energy reduction behind the shock. And so this is the first fundamental thing, that you can have a strong impact on the line curve. The second thing is that the radiation will be reprocessed in the CSM, and you will have what I've described earlier, which is that if you have basically an optical depth of 10, you will have 100 scatterings before getting out. And in most plasma, 100 scatterings means that eventually the photons will be absorbed. And so most photons that are emitted behind the shock here will be reprocessed by the unshocked CSM. And this is why you get these narrow profiles with broad wings. Okay, so now I get to the parts about the modeling. So this is work I've been doing since 2003 with John Hillier from the University of Pittsburgh. Originally, John Hillier wrote this code, CMFGen, for Wolf-Rayet stars, hot stars, O stars, OB stars, luminous blue variables like Eta Carina, and so on. In 2003, we modified the code to basically tackle the conditions that are suitable for supernova ejecta. And it's not completely different, which is why it was not necessarily so much work in redesigning the code so that it would work for supernova, because there are many things that are analogous between stellar winds in Wolf-Rayet stars or LBVs and the supernova ejecta that we see in type 2s or type 1s and so on. So the code is a non-LT, non-local thermodynamic equilibrium code, and it solves this set of equations. So you have the rate equations or the kinetic equations for the gas, basically tell you the level populations as a function of the rates that populate and depopulate these levels, and it includes all the microphysics, collisional processes, recombination, photoionization, charge exchange, and so on. Added to that, you have charge conservation. It solves the radiative transfer equation, so actually the 0th and 1st moment of the radiative transfer equation, which are written here in a time-dependent form, like these ones. And then you have this energy equation that tells you how much there is, how much energy exchange there is between the gas and the radiation. You have these coupling terms here. And you have additional terms that can be used quite flexibly. So typically what you have in supernovae, you have to account for radiative decay. It's very important in type 1 supernova, but also in type 2 supernova at late times. But here you can put various things. You can actually put interaction power if you wanted to. You can have magnetar power, fallback accretion onto a black hole, and so on. And so this code is quite sophisticated. It works transparently for any type of ejecta, type 1A or type 2, and so on. And so you just have to change the initial conditions for the ejecta, but the basic algorithm is the same. So the way the code works is that you start from a guess on the initial conditions, and then you convert to the solution by doing Newton-Raphson technique, by doing corrections on your initial guess. And it does this both for the level populations and for the radiation field. The radiation field is solved at 100,000, 200,000 frequencies, so it's very detailed. It treats accurately the radiative transfer in lines and in continuum, and so on. So you basically get, as a function of time, you will see the spectral evolution of a given supernova, and from that you can calculate the bolometric luminosity, the multiband photometry, and so on. In the context of interacting supernovae, what we need to do when we model these objects is that we need to develop a hydrodynamical model of the explosion, because the dynamics of the interaction is very important. So this is not a coasting ejecta that you're looking at. You're looking at an ejecta that will ram into CSM. There will be formation of a shock, and then there will be potentially a strong reverse shock, a forward shock, and the radiation might be very strongly out of equilibrium with the gas, and so you need to follow these things. The temperature that will result in these dynamical simulations is largely reflected by the presence of a shock, and so you cannot just assume that you have radiative equilibrium or things like that, which is sometimes used in stellar atmospheres. Well, it is used in the stellar atmospheres. Here, the temperature that is left behind in your structure is a direct reflection of what happened in dynamics, what the shock has done. So for this, we use, so we have this partnership between Heracles, which is code that was written by Gonzalez, Audit, CEA, and we basically combine the assets from that code and those from CMFGen. So what we do is that we do the radiation hydrodynamics of the interaction simulation with Heracles, and then we post-process with CMFGen. And we basically use the density structure, the temperature structure. We fix the temperature when we do the simulations in CMFGen. When we focus on these objects. So typical initial condition that we have, which I'm going to talk about in the next slides, is this structure. So this is a Eulerian code. So you need to define the initial conditions for your grid, for the velocity, temperature, or energy, and then the internal energy, the density. And so this is what it looks like here. I'm taking a red supergiant star just before shock breakout. So what you see here, this is in radius. The surface of the star is here. The shock is just about at the surface of the star. So this is the forward shock. We have a reverse shock going into the inner parts of the ejecta. And you can see here in the temperature is 10 to the 5, 10 to the 6. So there's a cold core that will be heated by the reverse shock. The forward shock has reached the surface of the star, and then you have your cool CSM here. And in density structure, you see this better. So this is the dense star, basically has just been shocked, and this is the CSM, and it has this shape, just to make it dense enough to have a strong interaction. And so if you let the simulation evolve, this is what you get. So you have 3 columns for different times. This is 0.5 days after the start of the simulation, 2 days, and 8 days. And this is the temperature, the velocity, the density, the optical depth, and the luminosity. So when
here the velocity is not clear, what is the typical velocity?
So this is in units of 1,000 kilometers per second. So this is 8,000, 9,000 kilometers per second here. So this is a good tracer of the location of the shock. So you have a bit of pre-acceleration from the radiation that's leaking from the shock. So there are lots of information here. So if you look at the luminosity, for example, this is the location of the shock. You have a huge rise in the luminosity. The reason why these curves are a bit complex is because it's time dependent. So this is not in radiative equilibrium here. You had a burst and it's crossing the grid, and it's crossing it on the light crossing time scale. It's at the speed of light, but it's optically thick. So this group, the different curves here correspond to different groups. This is the group that corresponds to the Lyman continuum. So there's a larger optical depth for that group, and so it propagates slower. But the other ones here correspond to low energy groups, and they travel faster. And one thing that you see here is that this rise in the luminosity, this pulse, this radiative precursor, is raising the temperature in the outer parts of basically in the CSM, ahead of the shock, which is here. And this is the location of the photosphere, this dot. And so here you have an optically thick CSM. It's been ionized, it's above 10,000 degrees, but it's not moving. And so this is the typical conditions where you have these 2 N signatures coming up, these narrow line profiles. This is at a later time. So ahead of the shock has moved a little bit. The radiation now in this CSM is in radiative equilibrium. Basically, there's a constant luminosity with radius. Your photosphere is still located here, and your shock has moved down, as you can see. And the temperature is quite high everywhere. Temperature is going down now as well in the ejecta because it's expanding. And this is at a later time at 8 days. So the shock continues to move out. The photosphere is now in the dense shell that was made from the swept up CSM and the ejecta. It's basically material from both regions. and then you see the luminosity, and then this, so you start seeing a lot of radiation coming out from the inner parts of the ejecta. And so you can do these simulations for all types of configuration. So this is the results from simulations in which we assume a low density CSM and a high density CSM. And this is showing the spectra that were computed in the post-processing step with the CMFGen, with the radiative transfer code. And so what you see here are rectified spectra as a function of time. So in the case where you have a low density CSM, you don't see any narrow lines from the unshocked CSM. All the lines that you see are all blue shifted with respect to the rest wavelength of the dominant ion, producing a line. So you have O6 here. This is carbon 4 and some helium-2. This is carbon 4. There's O5 here. They're all blue shifted because you're looking at a fast-moving material. It's optically thick. You're only looking at material moving towards you. You don't see the backside of this material. So all the emission and the absorption is biased towards the blue side. But if you have a high density CSM, like in the simulation that I just showed, then what you have is first a phase during which you see only narrow lines processed in the CSM. And eventually you see the formation of the whole spectrum within the dense shell. So you don't get any emission, mostly blue shifted absorptions. And eventually the dense shell turns optically thin and you see what is below. And then you have the same configuration as at top. So this is one clear explanation why you have this temporal evolution in the spectra of 20TLF and other type 2N supernovae. So this is a model, slightly different from the one I've shown, but for 20TLF, what we basically propose is that the pre-supernova, so the model that works best, suggests a pre-supernova mass loss of about 10 to the minus 2 solar mass per year, all the way to 10 to the 15 centimeters. And this way you can reproduce this peak in luminosity. The brightness here suggests that the progenitor was indeed much larger than a typical red supergiant star, so between 700 and 1,000 solar radii. And this is the comparison between the model and the observations, which suggests that the model is doing quite well. And this is comparison between observations and the model I've just shown. So in red you have the model, and the black is the observations. So this is during the phase when you have the narrow lines, and this is later on when this CSM has been completely swept up and you see the underlying ejecta. And these are observations at late time from this object. And as I said, this is kind of unique. This is a phase where you can see the inner parts of the ejecta. So this is when the phase when you see the metal-rich part of the ejecta. The fundamental signature of mass in a massive star is the amount of nucleosynthesis that it does, in particular prior to explosion, how much oxygen is produced. And so the oxygen line that we see in this nebula phase spectra are basically tablet forbidden line sits here at 6,300 angstrom. And the observations are in black, and these are various models in colors that correspond to different masses. As you can see, as you go from 12, 15 to 19, you increase the strength of that line, all else being the same. And these are simulations that I did in 2021. It's the same conclusion. As you increase the mass, this line flux increases. In order to explain the weakness of that line, you have to invoke a low mass progenitor. And so this is a bit of to me, is the first direct evidence that you can have interacting supernova associated with low mass massive star. Historically, people always thought that the objects that had produced this interaction had gigantic mass loss rates. They were the highest mass for supergiant stars, like the VYCMA, for example, objects that are really crazy. But here, this is a 10 solar mass star. It is nothing exceptional, and it has this crazy behavior. So this is really a change of perspective.
Can you exclude that there is a sort of binary, another star which may interaction or something?
I mean, so many people say that whenever you see a single star, it used to be a binary and it's a merger. And most of the time when there is binary, then you can see the influence of the binaries. For example, if there was a companion in this object, it would have lost its hydrogen envelope. It would have transferred it. It would not be today hydrogen rich. Or for example, it would have had no hydrogen lines early on, and then eventually would have rammed into hydrogen rich material would have had something peculiar. So the general idea is that these stars are probably intrinsically, so they're hydrogen rich and they do everything on their own. You know, they have this various instabilities that give rise to the mass loss, and then they explode, and then they create the interaction on their own. It's hard to say. I mean, in binaries, it's clearly you can have from an envelope evolution. You may have shed of material around the object and produce some interaction. I mean, here it's not needed to explain this thing. It's okay. So I don't know how much time I have. We started.
Not a lot. Yes.
I'm sorry.
Yes, we started 10 minutes later, so maybe we can. Well, maybe if you can start to wrap up.
Okay,
well,
so let me go quickly. So, if you want to bring diversity, if you want to explain the diversity of interacting supernovae, it's actually very simple. But just arguing that you have two parameters that control the whole thing, at least from the numerical point of view. What you have is the power source. You can change the explosion energy. How much energy is there in this inner shell that comes and interacts with the CSM? The second one is how much mass there is in the CSM. That's basically the extractor of energy. And if you increase the CSM mass, then you have a potential of going up to 100% efficiency in extracting the kinetic energy. So this, for example, what has been proposed for 2006 GY, which is a very famous interacting supernova. People suggest that this is actually a type 1a supernova. There was a white dwarf that rammed into 20 solar mass of hydrogen. So that's actually a scenario for a binary. And here the mass ratio is completely very contrasted. You have a 1 solar mass ejecta, energetic, ramming into 20 solar mass of material, and you have essentially complete deceleration of your ejecta. So, a typical type 1a supernova has 10 to the 51 ergs, and then you get all that in radiation. And indeed, in 2006 GY, the time integrated volumetric luminosity in the heaven is close to 10 to the 51 ergs. So it is possible to produce this thing. So here, this is just an experiment varying the explosion energy and the CSM mass. And what you can see is that you can produce things that have peak luminosities are enormous. This is 10 to the 45 ergs per second. This is huge. This is an object in which the kinetic energy from the inner shell was very large, and also you extracted most of it. And then you can vary the length scale for these interactions. And so, from a theoretical point of view, it's very easy to explain pretty much every interacting supernova. What the difficulty is to bring a consistent picture that match, what we understand from massive star evolution and explosion. So one thing that is very interesting to look at is to reduce the problem to just looking at the evolution of a specific line. So for example, H alpha. How is this line evolving in time? So in the simulations that I've shown and the observations, one thing that we typically have is that the line usually at the beginning is narrow, and then there's no line, and that's when the photosphere forms in the dense shell of swept up material, and then the line broadens eventually. And this is like the typical configuration for an interaction. You're looking at an ejecta, which is quite energetic. It rams into CSM that is not necessarily very massive. The CSM cannot decelerate completely the ejecta. So initially, you see reprocessed radiation from the CSM. That's you get the narrow lines, and eventually the supernova wins. It just takes over this CSM, and then you see the broad lines that are Doppler broadened. But in some objects, you see something like this. This is a 94W. It has a peak luminosity equivalent to a type 1a supernova, 10 to the 9 solar luminosity for like 3 months. But very strangely, it showed narrow lines at all times. And this is one example where you have to invoke complete deceleration of the ejecta. And so this is one model we produced in 2016. But basically, we say one possible mechanism is that you eject most of the hydrogen envelope in the progenitor, and then you have a low mass, very energetic explosion that gets completely decelerated by this ejecta. And then you have a much larger efficiency of kinetic energy to the conversion of kinetic energy to radiative energy. So there are 3 possible mechanisms that are argued currently. They're all well. The pair instability pulsation scenario has been known for quite a while, but these 2 here are quite recent. And so I will go briefly about this. Wave excitation. So this was proposed by Quattarchiotto and Fuller in the last 10 years. So the basic idea in a massive star, you have a burning core, you have convective, very strong convective motion in the core, and so you have lots of turbulence and wave excitation. And so gravity waves that are emitted in that core travel through the core and then get partially dumped, but tunnel through this helium burning layer, and eventually dump the energy. So they come out as acoustic waves, and they dump the energy in the hydrogen envelope. And in the simulations that Fuller has done, this is the luminosity versus time until core collapse. Then it shows the various burning stages here. This is the total nuclear power released by the core. This is the surface luminosity. There's a huge offset. Most of this energy is actually taken away by neutrinos, thermal neutrinos. But there's also a lot of energy that comes into convection. And then if you assume that a certain fraction of this power goes into waves, then this is the typical wave power that you can inject. And this is very large, much larger than the surface luminosity. And this power, when so in simulations that are depicted here, you can basically implement this power and see the effect on the density structure of your object. And so the energy that you dump at the base of the hydrogen envelope here creates this cavity, and it shifts the envelope to larger radii. It modifies completely the structure of your star. The basic reason why this power from waves can really alter the structure of a red supergiant star is because the binding energy of a red supergiant star envelope is very small. It's about 10 to the 47 ergs. So the core is highly bound, 10 to the 51 ergs. But the envelope is loosely bound. So any energy dumped in there can really have dramatic consequences. So if you have an event like this, you basically shed the envelope and then it's gone. And then the core continues to evolve all the way to core collapse and then explodes. And then you have interaction of whatever residue you have here with this material. That's your interaction. So you can also have nuclear flashes. So this is something that happens at the interface between low mass stars that become white dwarfs and high mass stars that form an iron core. And so in this regime, which depends on the code you use, but here this is the results in Kepler and the code of Woosley. So if you are above 10 solar mass, you have stable central burning, and then you form an iron core, and nothing really special happens. But between 9 and 10.3 solar masses, you actually burn off center in degenerate conditions, and you can have flashes, you can have deflagrations, and so on. And this is the history of the burning in the 10.5 solar mass star. This is the time until core collapse, and you see that this is all very nice, and you have clear phases of ignition, and the star is basically in a hydrostatic equilibrium. It doesn't care. But in the 9.5 solar mass star, what you see is that each of these nuclear events correspond to flashes, and then you have these runways where you have a lot of energy generated. The energy that can go into a silicon flash can exceed the binding energy of the hydrogen-rich envelope, and so it occurs an ejection. So this is another way of producing these interactions. And then the final one is the pair instability pulsations. So this has there was lots of excitement in 2000, 2005 when people were saying that the first stars in the universe were supermassive, because we knew from the 60s that if you have supermassive star, there's a special phenomenon that occurs. The central temperature of your supermassive star is really, really high. It's so high that you can actually get annihilation of your photons, of gamma rays, and produce pairs, electron-positron pairs. And the problem when this happens is that you transform radiation pressure into rest mass. You have your energy in the radiation that goes into rest mass, and so there's a pressure deficit whenever this happens. And so this leads to a contraction of the star and the thermonuclear runaway. So depending on the mass of the helium core, when this happens, you can have a complete disruption of the star and what we call a pair instability supernova with a gigantic amount of nuclear burning, 10 times, 100 times more than what you get in the type 1a supernova. But if you are intermediate masses between 30 and 64 solar masses, this pair instability is not violent enough to completely disrupt the star. And so instead of that, you have multiple pulses. And these pulses can be very, very chaotic. So this is a 44 solar mass helium core and 50. And this is the time to collapse. It's different scales. But here you can have these pulses, which is represented here by the central temperature. Any contraction corresponds to a spike in the temperature. And these actually have a recurrence rate of a day. And so they're basically they will all merge together in terms of influence on the envelope. here there's a delay of about 4 months between these pulses, and so there is time to eject the envelope in one pulse and then have another pulse that will ram into it, and so on. The idea is that after these pulses are over, the star just continues to collapse and forms a black hole. And there's been also a lot of interest in those objects because they are potentially the progenitors of the massive black holes that are seen in gravitational wave. That are seen in gravitational waves.
Regarding this, has been this observation of 19, I don't remember which is in the gap. In fact, the mass of the black hole has this changed somehow the model that you're
Well, I
explaining?
mean, here this is not really we're not really how can I say tuning the model to match the observations. This is just a qualitative presentation on the possible mechanisms. But so for these pair instability pulsations, we think that perhaps this object is suitable to explain this phenomenon. The people who do stellar evolution believe that this pair instability cannot occur at solar metallicity. Basically, the stars lose too much mass, and by the time they would be ripe for having the pair instability, they're just too light, and so the temperature is not high enough. And so this is under debate. I think it's not really, we don't really know. Well, and these are my conclusions. So there's a lot of diversity in interacting supernova. I've talked just about few objects. There's also one problem in the supernova community today is that the observations of supernovae has become a very professional activity. So you are either in the consortiums that do these observations, or you're out. And so I'm out. I do modeling, but I don't do observations. I don't know how much they observe, and so this you have to wait until publications come out. So the real number of interacting supernova isn't clear. The second thing is that there are many objects that may be interacting for just a few days, like the ones I've shown, and so they interact for a few days with circumstellar material at the surface of a red supergiant, for example, and then there is no signature of interaction. So there's the question: how do you classify these objects? And this is not very interesting topic. But, then the problem is that it has an implication whether you define an object as interacting or not. The criterion is very important for understanding the overall implications for massive star evolution and so on. And so one thing I find really exciting about interacting supernova is that the radiative transfer is really exotic. There are lots of very interesting things. You have multiple regions producing radiation. So you have, for example, you have high ionization stages and low ionization stages present in the spectrum. You have broad lines and narrow lines at the same time. It's really it's very exciting to work on these things, but it's also very challenging. So we have mass loss rates that are really enormous, as I said. This is 10 to the 5 times larger than for beta joules. The mass loss rates that we put in stellar evolution codes are steady state mass loss, and they represent just what happens when you have a radiation-driven wind at the surface of a star. Perhaps aided by molecules and dust and some things for red supergiants, but you are really far off the mass loss rates that are inferred in the objects that I just talked about. These mass loss rates are not implemented in any massive star evolution code. So there's this issue about how predictive the stellar evolution models are. And the mechanisms that I've talked about, this is all exploratory, and it will be a lot more work. But one thing that needs to be done, but one thing that is very interesting is to investigate the implications for the neutrino explosion mechanism. Because again, people use very idealized progenitor structures, 1D stellar evolution code. But what is the effect of having these potentially flashes or having this wave excitation emitted from the core? You may have an asymmetric core when it collapses. You may have also asymmetry in the distribution of the metals and so on. And so this may have implications for the way the massive stars explode afterwards. And so one final note is that historically people always thought that these objects, supermassive objects, were the progenitors of interacting supernova, and we have clear evidence today that they are interacting supernova over a huge mass range, from low mass stars, potentially even associated with white dwarf explosions or surface detonations and things like that. So it's very, very diverse. And that's it. Thank you.
Very interesting and pedagogical talk. So we already had many questions during the talk from the room. I don't know if there are some more or if there are questions on the chat on Zoom. I don't know if someone. Oh, sorry.
It was the first.
One.
Okay. I have just two small questions. I hope that your calculations of ready to transfer is done in spherical symmetry.
Yes.
Because then, if you see the system in different angles, you have to press also.
Yeah. Yeah, absolutely. And so, the question of asymmetry is very interesting. So one way of addressing asymmetry is to do two different 1D models that represent, for example, the conditions if you had an axisymmetric experiment, for example, what happens along the pole and what happens along the equator. So you can do one 1D model for the polar direction and one 1D model for the equatorial direction. And then we have 2D radiative transfer codes to combine these things. So that we can evaluate the influence of asymmetry.
The second small question. What about rotation inside the core? How it acts to produce stable or unstable situations for the stuff?
Yeah, well, yeah, sure, rotation, yes. Yeah, so I mean, so for example, when I talked about these nuclear flashes, so they're off-center ignition points. I mean, in 1D, there are off-center ignition shells. But in reality, the most likely points, and it's not clear how for example, if you have a deflagration is not going to go as a spherical wave going inwards towards the center of the star. It might go like, as a spherical, blob in all directions, and it's not. Yeah, I mean, asphericity is a major problem for everyone. So it's not just for the radiative transfer, for massive star evolution, for explosions, and so on. Yeah.
Maybe so. Nikos, they want to ask a question.
Yeah, Luke, thanks for this nice talk. This interaction with the circumstellar medium, could this affect also type 1a supernova? After all, they interact with the wind of their companion, the red giant, or whatever star they are interacting. Would it affect their luminosity and the evolution of their luminosity? Because, as you know, type 1a supernova is very important for cosmology.
Yeah, so you're absolutely right. So there are, I would say there are two things. So we know of type 1a supernova that have clear signs of interaction. We see hydrogen, strong hydrogen lines, so we know that there is stuff around, and so this is under study. But there is the possibility that you would have you could have CSM that's optically thin, and then you would not see it. And this is a big issue for distance determinations with type 1As right now. People don't really know whether you could have a contamination in light in the optical, for example, biasing the luminosity of the object. One possibility is that if you had interaction, most of this radiation would come out in the UV, and so you would not change the brightness in the optical. So that's one possibility. But yeah, this needs study. Yeah.
Okay, thank you.
No, okay, just a Brigitte Roca tells you many thanks, Luke, excellent talk. So, okay, if there are no more questions from the Zoom people, then let's thank the speaker again. Okay, thank you.
It sounds very exciting. All those explosions. Je pense que le problème avec les salles de séminaire, c'est qu'ils n'ont pas vérifié après le